I'm Fred Starr. I'm having to give this talk on behalf of David Dulieu. This is a version of what he would have given. He's given me a set of notes which are metallurgically beyond me. So just to give you an idea of what you've missed is that David was graduated from Leeds University. He then became a visiting research worker at Swedish Institute of Metals Research. And some of you who've got an interest in alloying sort of iron metallurgy will recognise that if you wanted the very best iron and iron ores in the 17th and 18th century, you imported them from Sweden. Sweden has managed to keep hold of its metallurgical industry, whereas other places have not. Anyway, getting back to David, he was with BISRA, the British Iron and Steel Research Association, for quite a number of years, and then moved over to British Steel Swindon labs, as I had to keep correcting our typists when I had some research going on there. David then joined Investors Sheffield, who had taken over the stainless steel making up in Sheffield, and he was there until retirement. David actually forgot when he sent me his notes to say that he's recently published a book on the history of stainless steel, and you are missing somebody today, I can tell you. But I'm sure that we all wish David the best. I spoke to him yesterday, and he was in a much better frame of mind than he was 2 or 3 weeks back, when he thought he might be going for something quite serious. Anyway, you see the title, and some of these slides I've put in myself. I don't have to really explain what this is all about, but you've got steamships, steam locomotives, and that's not a steam engine in the left-hand corner. That's a high-tech development, the gas engine. I mentioned just earlier about the power gas company on the Teesside. That supplied gas to go into that type of engine. But I'd just like to step back and put yourself in the shape of a 19th century, late 19th century engineer. Mild steel was really quite a novel material. It had only been around for about 30 years. Before that, you had wrought iron, which was really quite an expensive material. I'd put it in, probably in price terms, on the kind of level we've got aluminium today. And if you went a bit further back, before wrought iron has been made by the court process, you'd be talking about iron or steel on the same sort of price level, I would guess, as titanium. So when you look at these things and you say, well, it was just made of things are made of cast iron and mild steel, in actual fact, those people were right on the leading edge of technical development. And let's not sneer at them, because that's what they were studying. Now, that was before the First World War. This is what happened afterwards. You saw the kind of technology that people had before then. Look at what you've got in 1920 and 1930, as we've just heard. We've got the Haber-Bosch process. We've got nitric acid manufacture. We've got planes which are really properly designed. we've got mass production of automobiles. And then we've got steam turbines. This is at the bottom of this network of the network of grid in the northeast. This at the time was the most advanced power plant in the world, and it was using steam at 370C and 475C PSI pressure, much above what you'd expect to get in an internal combustion engine. None of these things would have been possible without the developments of steel and mass production of high-quality steels in World War I. Now, David asked me to emphasize this point. Here is a small collection of shells which I would guess would have been fired off within a couple of minutes of a bombardment in the later stages of World War I. And you see the kind of development that was going on. The British Expeditionary Force went to France and it got 410 guns, and I would guess that probably the average age of a gun was probably about maybe 5 years, maybe even 10 years, because people didn't fire off the guns very much. But you go to November 1918, you've got over 6,000 guns, 15 times as many, but those guns would be wearing out because they were used all the time. And similarly, if you look at the kind of shells that they were firing, there's nearly 1 million shells fired in 24 hours. So, although we're talking about the similar kinds of material that were being built, being fabricated before World War I, the great thing about World War I, accepting the development of more sophisticated steels, which I'll come to later, is that you were producing materials in mass production in a way that had been never imagined before. And it was that capability which started to transform what we could do in the new technical age that was coming. Now, this is the kind of thing that that people were having to go through during the pre-war era. That the Navy, which was the leading outfit interested in high-strength steels in a big way, was concerned about the quality of the steels. So they resorted to this wire wounding technique where you've got a gun barrel and in a sense, because you're frightened about its properties, you actually strengthen it by winding it full of wire, and this is cutting up an obsolete barrel towards the end of the war. This is what happens if you haven't got good quality materials. This is an explosion in a gun. The shell misfired, and the gun is split. Now, guns will split, but I want you to look at those lines which are in the picture. Each of those lines represents a line of weakness. It suggests that there is something amiss with the steel quality. And it was steel quality and it was steel quantity that was critical in World War I. Manufacturing was a big issue. You were talking about huge amounts of steel, 120-ton ingot. I would guess from my knowledge of the steel industry, you were talking about starting off with an ingot about this sort of square-shaped size, running from round about here to the wall over there. massive amounts of material requiring heat treatment, machinery, then again, because even so, they're worried about the strength of the material, they were doing the wire winding technique, and then you've got final heat treatment, etc., etc. Now, all of these things, the development of steels really came about because in the late 19th century, with the development of chemistry and chemical engineering and smelting practice, a variety of new elements were coming onto the market which could be incorporated into steel to strengthen the materials. And chromium was about, first this came in round about, between about 1875, 1880, and that was used in early gun barrels. Then we got nickel, which gave strength. Chromium tends to give hardness and good strength, but it undermines toughness. And then you have combinations of the alloying elements, and by 1940, molybdenum and vanadium were coming in. Now, all of that was driven by the armaments industry. There was very little interest by people in ordinary commercial life. They just didn't need this kind of thing. But the armaments industry only required quite small amounts of this. The thing about World War I is that you've got this multifold increase in demand. Now, metallurgists tend to concentrate on the alloying elements, but it's not just the alloying elements. If you're producing something like a gun, you have to forge something to the right shape. But when you're doing the forging, if you do the forging properly, it removes inhomogeneities in the metal. You get the right directional properties. If you think about that gun barrel that had gone off that I showed earlier, that was and had not been forged properly. And then you've got the heat treatment. And you're doing that to get the right combination of toughness and hardness. And in some pieces of equipment, as I show, you want different amounts of each at different points, particularly in shells. And to do that, you need to know temperatures, you need to do timings of heat treatments, and your oil and hot water baths for quenching and tempering have got to be properly controlled. These were all things which you took out of the hands of the craftsman and you turned it into something whereby anybody could do it, providing they're given the right instructions. All of us have opened a cookbook. Anybody who has done A-level chemistry can cook. Because all you have to do is to follow the recipes. And it's the same when you're producing steel. I mentioned the sophistication of heat treatment. Well, I won't go through all of this, but here you've got a shell where the hardness is ranging from 600 Brunel at the tip, about as hard as you can get it, to something which is pretty hard near the base of the shell, where the shell is being driven forward by the cordite in the gun barrel. And to get all of this, you need right heat treatment at the right points. To be able to do this, you need a physical metallurgy lab with microscopes, pyrometers, sophisticated apparatus if you're trying to develop new alloys. Now, If you want reliable steel, you've got to have all of this done. These are things which are as true today, as true yesterday as they are today. Good steel making, good casting and processing, and good heat treatment. What did you have in the early stages of the war, particularly in this country, which, as I said this morning, this country was industrially backward compared to its competitors, and we shouldn't forget that. This is what you were trying to make steel with. Well, it's actually an open hearth plant. This is a modern one. You wouldn't have seen this scene in 1900. Actually, I saw scenes like this when I worked in the steel works. In fact, I once got a shoe full of melted steel in a similar sort of, I ran the back of the furnace. I'll tell you that story on another occasion. But here is steel slopping all over the place. You're not going to be able to make the highest quality steel with an open hearth furnace. Here are the open hearth furnaces at the time, with people chucking in alloy, scrap and so forth through the furnace doors. Here is another picture. You see this kind of scale of the thing. It's not really a very sophisticated way of doing it. You can make low alloy steels this way, but it's not the best. This is what you want, the electric arc furnace, and we were late in picking up the technology. Our first electric arc furnace came in around about 1910, 1911, but during the war there was a huge expansion. And as I was so glad we had the talk about electricity this morning, because it was electric power which made this technology possible. You've got much more sophisticated control over what you're doing with this type of furnace. Again, this is simply emphasizing the range of materials demanded by armaments. Nickel chrome steel barrels, these are low nickel, low chromium contents. Armor plating, even the hydraulic circuits are sophisticated because you're running at pressures of a couple of thousand pounds per square inch. You see, here is armor plating. Now, I don't know whether you can see the figures at the back here, but that is about the size of the man's head, and you see by my finger that the steel plate is thicker than a man's head. That is how sophisticated we were having to get. Now, we were having to produce, when the Haber-Bosch process came in, we were having to produce that kind of component because of the pressures and temperatures involved. Now, the other driving force that we had during the war were the new military technologies. And you start off the war, of course, with what you've got available. We have developed internal combustion engines, but if you look at the airframes, there was really nothing very sophisticated going on there. But it was interesting that Carl mentioned this morning that Germans were using steel tube aircraft structures, and we were still stuck with wood. But the engines, our engines were pretty good. They were using lightweight, highly stressed components. They needed high quality bearings. You've got a lot of centrifugal stress. This is called a rotary engine, and it had got to be strong and light. Well, how did they do it? Well, the cylinders has got to be, this is our air, being air-cooled, the cylinder is moving round and round and round. It's got fins on. What could they do at the time to make something strong, got good centrifuge, taking the centrifugal loads? They actually took a bar about that thick and about that long, and they bored it out in this fashion, in the picture on the right. That's been done, and then carved on fins. That is the kind of lengths that they were having to go to. We also had tanks with quite thick armour on. We had aero engines which were running at higher temperatures all the way through the war. And that leads me on to the one real development in steel production, in steels during the war. But even here, well, it all started with, again, an armaments issue. A man called Harry Brearley, who'd taken over the research labs at Firth Browns in Sheffield. He was looking for improved steels for gun barrels, and he was investigating various types of steel. Now, here's a kind of little anecdote, and I haven't shown this graph, but if you can imagine what is happening. Supposing you've got a steel, and you start adding a bit of chromium to it, 1%, 2%, and the 1% is quite good, the strength is getting better, 2% even better, 3% even better, 4%, oh, it's not so good, 5% is actually weaker. You come down to 6%, it's brittle as hell. And people would stop there. Well, Mr. Brearley decided to go a bit further than anyone else, and he started pushing the chromium level back up. But he was careful enough, unlike some of the other people, to use pure chromium when he was making his stainless steel. Up to around about 1900, you could not get pure chromium if you wanted to make an alloy steel. It was always containing carbon. Now that didn't matter when you were making a low alloy steel. In fact, a bit of carbon gave you some extra strength. But if you were trying to push the chromium content up, you're putting more and more carbon into the material, and it's the carbon that embrittles the material. Now, here you have a situation in which the development in one field improves what's going on in somewhere else. And it was the development of the whole Harrod process for the manufacture of aluminium, which then enabled pure chromium to be produced. And so you could, people who were doing steel development could play around with pure chromium. And Harry then started using pure chromium, and he got up to the 12% level. The story is that he chucked out these test alloys onto a scrap heap. Some of them didn't corrode. That is not true. He was a proper researcher. He looked at the microstructure. He etched up the materials. Each time he made a new cast, he etched up the materials, and he found that those 12% ones, the acids he was trying to etch them with, they weren't touching it. He had to use stronger acids to reveal the microstructure. And he began to think, well, maybe these are going to be very, very good corrosion-resistant alloys. And his initial market was the upmarket manufactured knife blades. Well, I'm not sure how well he would have done in that field, because the only people who could have afforded knife blades at that time would have been the ones in the country houses and so forth, who had got plenty of servants to polish up the rusty old knife blades. And the people like down at the bottom wouldn't have had the money to buy this. So in order to get production, you needed another market. Well, that other market was exhaust valves. Now, if you want another lecture, I'm quite able to give you a lecture on the developments of exhaust valves in aircraft engines. And there is a part 3 of my saga of the exhaust valves coming out in the Newcomen Journal very soon. It's only taken 6 years from start to finish to see this happen. It's taken longer to get the paper published than it was to Harry to get his exhaust valves made. So there was great excitement in the aircraft engine and steel manufacturing community when they realised that these high chromium valves, which were very good at high temperature, very good oxidation resistance, and a whole set of other materials started to be developed. You have really the two classes, the martensitic, which are now regarded as being the cheapo, high-strength valve materials, and the rather better ones, which are austenitic, which contain nickel as well as chromium. All of this efforts to manufacture steels, low alloy steels, high alloy steels, resulted in confusion, and so it was decided, well, there should be a few established standards, and that started in 1917, and it's those standards which have carried on to the present day. So those were for aircraft, and those materials eventually penetrated normal life. As well as exhaust valves, stainless steel strip was used after the war for aircraft construction. You've got quite sophisticated sections of this type being made by companies like Bolt and Paul. And you also got, again, rolled thin sections. That technology was then taken over by the aluminium people, who used the same sections for duralumin. Steel in aircraft then began to rather fade out. We're now at well into the post-war era. Hadfields were determined to keep ahead of the competition. They tied in with a French company to work on austenitic steels, particularly for steam turbines. And they're very, very useful in the back end of the steam turbine, where you've got a lot of blade erosion from water droplets. And that's how Britain entered the 20th century. Thank you very much.